Welcome everyone. This is the third webinar in this summer webinar series that we have been organizing. And when I say we, this is organized by INYAS, the Indian National Young Academy of Science. INYAS is a part of INSA, the International Science Academy. And one of the mandates of INYAS is to do outreach activities for school and college students in all of the sciences, as well as maths and engineering and medicine and so on. So with that mandate, we thought that it would be nice to have some webinars in the summer when students have break from their studies. And we are very pleased that five very distinguished speakers agreed to give the talks. And today we have Professor Prerana Chatterjee. She's currently at IIT Madras, but she's moving very soon to NISER Bhubaneswar as an assistant professor. Prerana did her PhD from TIFR, and after her PhD, she did several postdocs for instance, at the Czech Academy of Sciences, Tel Aviv University, and she was also a visitor at IIIT Hyderabad, as well as NISER Bhubaneswar before moving to IIT Madras. Her work is in theoretical computer science, and today she is going to speak about Alice, Bob, and some bags of cash. Over to you, Prerana.
Thank you so much for inviting me. So yeah, today I will be talking about some games, a couple of games, but mostly one game, okay, which in uh, it yeah maybe I'll just get started with it and then we'll see what this game is. Okay, so we have two players, okay, two characters in our story, which is Alice and Bob. And throughout, essentially, what they want to do is get some cash. They want to win some cash, okay? And they have to play some games. And if they win the game, then they will get to keep the cash with them. Otherwise, they will not, okay? So let's do a warm up game. Okay, I must mention that this I want it to be a little interactive. So please think along as I uh, as the talk progresses, and also yes, please unmute yourself and ask questions if you have any. Okay, because I want it to. I mean, I want everyone to follow at least. I hope everyone follows the talk. Um, okay, so yeah, so Alice and Bob are there. They want to win some cash. The way they are going to win is by winning the games. Okay, so let's for a warm up. Let's start off with a simple game. Okay, so what is the gameplay? Alice and Bob are going to go into two separate rooms. Okay, and they are each going to flip a coin. Okay, so and they are going to either get a head or a tail. Right, so they go into separate rooms, flip a coin. Each of them either get head or tail, and they are just going to write down their own results. Then what they are expected to do is write down a guess for what the other person might have gotten with as a result of their coin flip. Okay, so Alice first writes down her own result, and then she is asked to, or then she's writing down a guess for what Bob's result could be. And similarly, Bob also first flips a coin, writes down his result, and then writes down a guess for what Alice's flip could. Okay, and when do they win? So if both the guesses are wrong, okay, then they lose. Otherwise, they both win. Is it clear? So they are writing their own result and they are writing a guess, right? So both, if either of them get it right, then they are both going to win and get the bag of cash. But if both of them are wrong, then they are going to lose and not get the cash. Okay, and just a note that throughout, actually, Alice and Bob are always going to be teammates. So it's a cooperative game. They are going to play this together, and before going into these separate rooms, they can actually meet and discuss what the strategy can be. But once they have been sent to the rooms, they cannot talk to each other. Okay, is the gameplay clear? So they are together, they discuss a strategy, and then they go into separate rooms. both of them guess what the other person's coin flip is going to be. If either of them is correct, they both win. But if both of them guess wrongly, then they both lose. Okay, what do you think a strategy can be? Uh, Explain in short. Okay. So you have Alice and Bob. Okay. Um, who are playing a game. Okay. What is the game? They first, let's say there is a 2 BHK. Okay. So in the hall, both of them are there together. They can discuss a strategy of how to win the following game. Okay. When the game starts, Alice is sent to bedroom 1, Bob is sent to bedroom 2. There is no way of them talking to each other. Alice flips a coin, gets either head or tail. Bob flips a coin, gets either head or tail. Okay. But Alice is now supposed to guess. Okay. Yeah, okay. Let me just finish the explanation. Okay, I would really like if people just unmute and answer, because it's taking me time to read the messages. Okay, so it's better if you just unmute and answer the question. Okay. Um, yeah. So just one quick. So okay. So both of them flip a coin, write down, get either head or tail. But then um, the point is that they have to guess what the other person has got. Okay. And uh, if both of them guess wrong, then they lose. But if either of them guess correctly, then they win. But I have some answers. Can one of you just unmute and say what you were writing? Okay, so who all were there? There's others. Others says that both will say either head or tail. So you're saying that so Alice will also, without doing anything, Alice will just say head, and Bob will also say head. Is that what you're saying? So Chetna is also, they both guess tail. Okay. Uh, right. But my claim is, in this game actually you can always they can always win. Can you think of a strategy where they can always win? So what others and Suchetna are saying is that, let's say both of them, without thinking or anything, they will just say, both of them say tails, for instance. Okay. So in that case, you will win with probability 75%. So you will lose only if both of them are head. You're right. Okay, which is great. So you're winning with 75% probability. But my claim is that in this game, you can actually win with 100% probability. Can you come up with a strategy? And please unmute, okay? So that I don't have to read it. And others can also, I think.
Hello, ma'am. Am I audible?
Yeah,
Yeah, I'm guessing just I don't know whether I'm correct or not.
of course, of course.
Yeah.
No problem.
So, if Bob is getting had, then he will say the reverse of this. That means he will
Okay,
get his tail. And
okay.
Alice, if Alice is getting had, then
Hmm.
he will tell the reverse of that. Because if
Oh.
both of them are getting the same, if both
Hmm.
of them are getting had, then they
Hmm.
will obviously win, right?
Uh, No, no. So the guess has to be correct, right? So both of them getting head head. If both of them do opposite, then both of their guess is wrong. So this is still.
Okay.
But you are yeah. So the hint is that you actually have to use your own result also somehow. So you are going in the right direction. Just think a little more. So maybe let's move on to. Oh, sorry. Oh, there's a lot of repeat of the same thing. I see. Yeah. So Alice and Bob are in different room. Alice. Oh, what happened?
Hello, ma'am.
Yeah, yeah. Just a minute. What did I do? Yes. Is it visible? It is visible. Okay. So Alice. Yeah. Okay. Sorry. This is all a repeat of everything. Right. Okay. So yes. Who was saying something? Please say. Hari Shankar. Was you saying something? Please go ahead. Somebody was. Somebody was saying something, right?
Yes, it was Hari Shankar. Yeah.
Please go ahead.
Hello.
What were you saying? Yeah, yeah. Go ahead. What is your strategy? Okay, maybe so. Okay, so I want little more hint of. You see that there are two cases. Okay, either Alice and Bob are going to have the same result, or Alice and Bob are going to have different results. Even though there are actually four cases of head, 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 tail, tail, head, tail, tail, you can divide it into just two cases of either both of them having same result or both of them having different result. Is this helping you somehow to come up with a strategy?
Yes, if
Yeah.
one of them one of them guesses that both of their coins are identical. So, let's say Alice says that Alice will write down whatever is on her coin.
Yes.
Bob will
Yes.
write down whatever is the opposite of whatever is on his coin.
Exactly. Exactly. Exactly.
So,
Great. Great. That is exactly what the strategy is. Okay. So Alice guesses whatever is her result, and Bob guesses the opposite of whatever his result. Okay, is that, I'm hoping this is sort of clear to everyone. So that there are these two cases of either Alice and Bob have same result or Alice and Bob have two different result, and the two of them are going to make sure that both these cases are like, so one of them is going to cover the first case, the other is going to cover the second case, right? So basically for the strategy, if in the head case, Alice is going to guess head, Bob is going to guess tail, right? But they are winning because Alice's guess is correct. Similarly, in the head tail case, Bob's guess is what's going to help them win. Tail head also, Bob's guess is going to help them win, and Alice's tail, Alice's guess is going to help them win. Is it clear to everyone? So in the case one, Alice is going to cover this case, and in the case two, Bob is going to cover it. Okay, I hope this is clear to everyone that in this game, actually, Alice and Bob can always win. Okay. So now that we are maybe warmed up with how Alice and Bob are playing games, let's actually move on to the game that I want to talk about in this talk. Okay. So it's a similar situation where Alice and Bob want to win a game and get some cash. Okay. But in this, there is an extra player. Player name, actually, it's a referee. Okay. And who's Charlie. So again, Alice and Bob are going to go into separate rooms. Okay. And now Charlie is going to first go into Alice's room, flip a coin. Okay. And let's say the result is X. So head or tail, X. Okay. And then he asks Alice to choose either whether she wants to keep the cash or not. Okay. He then goes into Bob's room and does the same thing. Okay. So basically, Alice and Bob are in two different rooms. In Alice's room, a coin is flipped, and she is asked whether she wants to keep or not keep. So like a 0 or a 1. Okay. So keep or not keep. And again, in Bob's room, there is a coin flipped. Either head or tail is the result. And he is also asked the same question. Do you want to keep the cash or not keep the cash? Okay. Now here's when they are going to win. So if both the tosses were heads, then they win if and only if they make opposite choices. Okay. So if both the coin tosses were heads, then they win if and only if they make opposite choice. So one of them says they want to keep and the other one says they don't want to keep. In every other situation, they win if and only if they make the same choice. Okay. And as before, they are teammates. It's a cooperative game. Before going into the rooms, they are allowed to be in the hall and discuss with each other what they are going to do. But then after they go into the room, they can't talk to each other. Okay. So just to put it in a tabular form, this is what the situation is. So there is a coin toss that happens in Alice's room. There is a coin toss that happens in Bob's room. In the case when both the coin tosses are heads, the winning situation is that one of them says keep, the other says not keep. But in every other situation, they win if and only if both of them say either keep or not. Is this game clear? Like, is the what is the game and when are they winning? Is it clear? And if not, ask questions. So if there are no questions, I'm assuming it is clear. Okay. In this game, can you what is a like, is there a strategy that you can think of that you are going to win in? So in this case, actually, this Adarsh and Suchetna's strategies in this case also is going to help them win 75%, right? Is that clear to everyone? If not, please ask questions. So what was Adarsh and Suchetna's strategy? That without doing anything, the strategy that they are going to apply is that both of them say that we will keep, right? So this is again repeat of the explanation. So Charlie goes, flips a coin, asks coin, yes, and okay. And this is, so the strategy was that similar, I mean, so this is the same strategy that Adarsh and Suchetna had mentioned for the previous game, right? So both of them, oh, how do we say 75%? Sure. So 75% because, so each of the head, tail, tail can happen with equal probability, right? So each of them happen with probability 1/4. Now for 3 of the cases, so head, tail, head, tail, all these 3 cases, they are going to win if both of them say keep, right? So 75% of the time they are winning. Is it clear? The only time that they are not winning is the head case, which will happen with 1/4 probability. So 25% of the time they won't win, but 75% of the time they will win. Okay. So they win with probability 75%. And in fact, you can show that this is the best they can do in the classical set, in the sense that even if they have access to some random bits, as in so earlier, so suppose first case I tell you that when they are allowed to strategize in the hall, they are not allowed to do any coin tosses there. Okay. In that, so the current strategy doesn't have to do any coin tosses. It's just a deterministic strategy, right? Because they'll just go and say keep. Both of them go and say keep, right? But let me allow them to actually have, like, during the strategizing, suppose they can do some random bits and suppose they can do some coin flips and make a strategy which is randomized. Okay. Even that extra power doesn't allow them to win with probability more than 75%. This is what is called Bell's inequality. We will not go into the proof of it. Okay? Let's just trust Bell. Okay, that even if they had access to coin flips while strategizing, they still cannot do better than just this simple strategy of both of them saying keep. Okay. Now the rest of the talk, which is the main part of the talk, what we are going to ask is what if they had quantum bits? So instead of coin flips, instead of random bits, if I give you a little more power, or what seems like little more power, which is quantum bits, can they do better? Okay. And so before we actually show what happens, we need to get a little comfortable with quantum bits, right? So qubits for short. So qubits, really the only way you can think of qubits is that they are a new data type. So just like you have integers, real numbers, uh, Boolean bits, things like that. Each of them are they are different data types, right? Or strings that you define in a computer program. Quantum bits are a new data type. You cannot think of them as anything, anything that is classical or anything that you have, that you have encountered till now. They are a new data type, and in this new data type, there are two basic values, which is a 0 and a 1. Ket 0, ket 1. So that thing is called a ket. Okay. So ket 0 and ket 1 are the two basic values of this new data type. And the magic of quantum is that a quantum bit can literally be in both these states. So a quantum bit can be both a 0 or a 1 at the same time before a measurement is made. Okay. So you can, so like randomness, you can think of as somebody has flipped a coin, put it in a box and has given it to you. Okay. And then when you open it, you figure out if that coin toss was saying either head or tail. Okay, that is what random bit is. But a quantum bit is you have a box, and you have to imagine somebody who is just sitting there who hasn't tossed the coin yet, who is just sitting there with a coin. You don't know what the result is till you open the box. When you start opening the box, the person is going to toss a coin and it's going to come out either a 0 or a 1, and you will see. Is so I want to spend some time on just this point, okay? Because it is you really have to understand that these are two completely different things. So please ask, I would really like to have questions about this, because it cannot be that you understood it. Yeah, okay. So maybe I will try to write something or draw something. Okay. So what I'm saying is that in a random bit, okay, a random bit is like you have a box, okay, some person has flipped a coin, and whatever the result it has put into either head or tail. So this is Alice, okay, and then she goes and gives this to Bob, okay. So but when she comes and gives it to Bob, there is already a result in the box, okay. The box already contains either a 0 or a 1. It's just that Bob doesn't know whether it's a 0 or a 1, right? So there is a coin which has been flipped, the result has been put into the box, and then Alice comes and gives it to Bob. Once Bob's opens the box, he figures out whether it's a head or a tail. But it's not like the answer was already there in the box. It's just that Bob didn't know. In the quantum setting, it is completely different. It is like there is a box, okay, and Alice is literally, oh, what happened? Alice is literally inside the box and has not flipped the coin yet. Only when Bob opens the box, or when Bob is going to open the box, Alice quickly flips a coin, and at that point it gets decided whether it's going to be a 0 or a 1. So till Bob opens the box, it is both 0 or 1. There is a probability of it becoming 0 or it becoming 1. Of course, this is a much very simplified version of it, but that is what the difference is. Random is that it has been flipped, the answer is there, you just haven't seen it. But here, nobody knows what the answer is going to be till you open the box, till you make a measurement. Okay, so in general, a qubit has the form of this. So a times 0 ket plus b times 1 ket. Okay, where a and b are numbers between 0 and 1, which has the property. Sorry, impact on result. Yeah. So we will see how. Okay, Sachin, can you just maybe let me finish this and then Sachin, please ask. I didn't completely understand your question. Okay, so a general qubit has the form of a times a 0 ket plus a b times 1 ket, where a and b are numbers which have the property that a square plus b square is equal to 1. Okay, so the probability, when a qubit which has the form a0 plus b1 has the property, so there is this Alice who is sitting inside the box, right? So the probability, so the coin is a biased coin. Okay, so it is going to flip 0 with probability a square, and it's going to flip 1 with probability b square. Okay, so it's like when Bob opens the box, this qubit is either going to get measured to 0 or a 1. Probability of it getting measured to 0 is a square. Probability of it getting measured to 1 is b square. Okay. Yeah. Now please questions. Yes, Sachin. Can you just unmute and ask what it means? So there is different impact on result in different. Yeah.
Am I audible, ma'am?
Yeah.
I'm just asking ma'am that you have just considered two cases now. So ma'am, the results are different. I'm just asking that results are different or same in both cases. As you have said that if we just flip the coin before, and if we just flip
Yes.
the coin at the moment, then results are different or same, ma'am?
No. So in some cases it can be simulated, but we will see that exactly. So this game that Alice and Bob were playing, we will see that if they have access to qubits instead of random bits, they can actually win with probability more than 75%. That is the sort of that's the main point of this talk. Okay, so we will see how this extra power of it genuinely being in both states till the very end is much more powerful than just you not knowing what the answer is. Okay, so we will see that. And Ria, can you also please, what means the current one? Ria, can you please ask what I didn't understand at all? What? No, so you don't have to guess anything. It is just that I just want to say that until you make the measurement, you don't know what the answer is going to be. So you don't want to guess. You want to use this power to improve your algorithms. Okay. So the aim is not to guess. The aim is that you want to use this power of quantumness that you don't so once we measure, it collapses. The state collapses to either a 0 or a 1. Okay, but you want to keep, so the whole point is that you want to keep your quantum state in a quantum state as far as possible unless you until you really need it. Okay, so you want to use this power of the quantum being in both states at the same time. You can, so similar to AND or NOT, so we will see. Okay, so similar to your classical gates like AND or NOT, you can have quantum gates, and you can apply quantum gates and keep it in a quantum state till the very end, or till you need to make up. Once you make a measurement, it has collapsed. Then it's like it has gone down to either a zero. Okay. Okay. So the other power that we will need is this power of entanglement. Okay. So two qubits are said to be entangled if they are not independent of each other. Okay. So what do I mean by that mathematically? So still now we were looking at just one qubit, right? So there is a 0 or a 1, but then you can have multiple qubits, right? So a 0 qubit is essentially just a 2 qubits. Okay, but now a 0 qubit you can actually write as a product of two single qubits, right? Whenever you can write a qubit in terms of a product of two qubits, they are not entangled. Okay, so I know it's confusing, but hopefully by the end of this slide, after the questions, it's going to become clearer. So similarly, if you have suppose a 2 qubit, so now okay, first actually tell me when you have 2 qubits, what are the basic qubits that are going to be there? What are the basic things? There is a 0 0 0 1 1 0 1 1. Those are the 4 things that are possible. Is that clear? So what am I saying? I'm saying that in the two case, there was just a 0 or a 1, right? When there are 2 qubits, then these are the possibilities. Is that clear? Is that clear? So now any 2 qubit system is going to be a linear combination of these things, right? So earlier it was just A times this plus B times this. Now we are going to have A times this plus B times this plus C times this plus D times this. This is what a 2 qubit system generally looks like, right? Similar to the previous case, right? So now we are just looking at some examples of 2 qubit systems, right? So in this case, in this case, it is so 0 0 is just like A is 1, everything else is 0. Okay, so that can be written as a product of two things, product of two single qubit systems. Because you can write it as a product of two single qubit systems, we say that this is not an entangled. It is not in an entangled state. Similarly, this is a 0 0 plus a 0 1. So this part is there, these parts are not there, right? So this again you can write it as a 0 times a, so this is this is a single qubit system, this is a single qubit system. You are writing them as product of two single qubit systems. That is why these are not entangled. So this thing is not in an entangled state. But now look at this one. Okay, so it's a 0 0 plus a 1 1. Okay, and this is something you should check, that there do not exist any A, B, C, D such that this can be written as, so there does not exist any A, B, C, D such that this thing is equal to A times 0 plus B times 1 times C times 0 plus D times. Okay, so this is something you should check. And whenever you cannot write one state as a product of two single unit states, it is said to be in an entangled. So this state is said to be entangled. These two qubits are entangled. Okay. So this state cannot be written as a product of two single qubits, which is why this is an entangled state. That is the definition of entangled. Yeah, now questions, please. Or is it? Maybe it's not that difficult. So basically, so a two qubit system is said to be entangled if you cannot write it as a product of two single qubit systems. And the most famous entangled pair is actually this only. It is called the EPR state. Okay. This is the most famous entangled pair. Pair because two qubit system. Okay, and just to note that, see, we have not normalized these qubits. Okay, so in the sense that if, just like in the earlier case, you had this a square plus b square had to be equal to 1. Here also, when you write this, I mean technically it should be like this, so that 1 by 2 root 2 whole square plus 1 by root 2 whole square should be equal to 1. So, but we will not normal. So whenever there is nothing written and you see that the squares are not adding up to 0, you should just assume that it has been equally spread out. Okay, so yeah, no, now I think I really want to stop for questions. Please ask.
Ma'am, can you repeat what exactly you mean by the product of two qubits?
So product as in, okay. So a single qubit, as saw, what is happening? A single qubit looks like this, right? Right? So a product of, so suppose I give you two qubits, then this is going to look like AC times 0, 0 plus AD times 0, 1 plus BC times 1, 0 plus BD times 1, 1. Okay. Okay. And in general, a two qubit system is going to look like A prime times 0, 0 plus B prime times 0, 1 plus C prime times 1, 0 plus D prime times 1, 1. Okay. So given A prime, B prime, C prime, D prime, if there exist A, B, C, D such that A prime is equal to AC, B prime is equal to AD, C prime is equal to BC, D prime is equal to BD, then this state can be written as a product of two single qubit states. If there do not exist such an A, B, C, D, then it cannot be written. And in that case, it's said to be entangled. So this Q2 qubit system is said to be in entangled state. Is that clear?
Yes, ma'am.
Okay. And yeah, so that's what entanglement means. And just to note, this normalization factor also, technically it must have the property that A prime square plus B prime square plus C prime square plus D prime square is equal to 1. That's always has to be the case, because these are the probabilities, right, with which things are going to show up. So unless they add up to 1, it's not a probability distribution, right? So, but if you see that these squares are not adding up to 1, you should always just assume that it has been split up equal. So these are the 2 points I want you to take away from this slide. What is entanglement, and that this I'm not going to normalize from now on. Okay, and this is the EPR state, very important. Cool. So now the question that, who was it? Somebody was asking, right? I think Sachin was asking, was that can every quantum experiment always be simulated using randomness? That is what his question was, right? And really, this is something that the first people who were, like figuring out this whole quantum mechanics, it really felt like, what is this spooky behavior? It must be the case that every quantum experiment can be simulated. And indeed, this is where the EPR pair was first defined in that paper. They said that really there is nothing spooky much happening. See, because this experiment, okay, so let's see the experiment that Alice and Bob is going to create an EPR pair. Alice Alice has access to the first qubit part of it. Bob has access to the second qubit part of it. And then Alice measures her qubit, Bob measures his qubit. So what is this going to, so what is this experiment doing, right? See, this EPR pair is a 0, 0 plus a 1, 1. That's what the qubit looks like. So that's what the two qubit state looks like, right? If Alice has access to the first bit and Bob has access to the second bit, and Alice makes a measurement and she gets 0, then you know that Bob must be getting 0. And if Alice sees a 1, it must be the case that Bob will also see a 1. Is this clear to everyone? Yeah. Okay, great. So because the two qubit state is 0, 0 or 1, 1. If Alice makes a measurement on the first state, it becomes a 0 or a 1. But if the first state is 0, then the second state has to be 0. And if the first qubit is 0, the second qubit has to be 0. If the first qubit is 1, the second qubit has to be 1. Right? Which is why this is something spooky is happening. So they are in two different, they have taken one qubit each and made measurements in two different rooms, and yet one person's measurement seems to affect the other person's measurement. But in this paper they said that no, this is actually nothing much spooky is happening, because this can be simulated using a random experiment, which is that you pick A randomly, you don't see what A is, but you just set B equal to A. And then A takes, this should be small a. A takes the first random bit, B takes the second, Bob takes the second random bit, and then they actually look at their individual random bits. It is doing the same thing as the previous one. Okay. So at least if the quantum experiment we were talking about was just Alice and Bob measuring their individual qubits, this experiment can actually be simulated using classical randomness, right? And people were like, oh, okay, then it must be the case that we are just missing something. Like quantum is essentially classical with some extra, we are just missing some hidden variables, right? But then came along Bell, right? And we go back to that game that we had started off, right? So what was the game? That Alice Bob were allowed to strategize, and they were sent to different rooms. So they were sent to different rooms, and then there were these coin tosses that happened. If both the coin tosses resulted in head, then they would win if and only if they answered different things, and if in any other case they were going to win if both of them, just a minute, I will come back to Lokesh. In every other case they win only if they answer consistently. Okay. And we saw that in the classical case, Alice and Bob were only, so Bell showed that, there is a simple algorithm to win with probability 75%, and Bell showed that this is actually the best that they can do. Correct? But now one can show that if Alice and Bob have access to an EPR pair, then there is a strategy that allows them to win with probability at least 80%. Okay, so this experiment was the first experiment which showed that no, quantum gives you extra power. It is not that you can simulate quantum using some classical strategy by being smart. There is no way in which, I mean, quantum is going to give you more power. Okay, so now coming back to Lokesh's question, can you just unmute again and ask? So are you just asking this? Yeah, I mean, so yes. Yeah, so this property that the EPR pair is actually entangled is going to help them win with probability higher than 75. If that's the question, yes, that's exactly what we are going to show now. Okay. Right. So again, before we go into the algorithm, we just need to play around with the EPR pair a bit, because there was this part that somehow Alice has, even though they are like an entangled pair, I was saying things like Alice has access to the first qubit and Bob has access to the second qubit. What does that mean, right? So again, similar to classical gates, let's look at some of the things that you can do to qubits. Okay, so on normal bits, you do these operations like AND, or NOT, things like that. Right? What are operations that are allowed on quantum bits or qubits, right? So let's look at one simple operation, which is, let's call it the toggle operation. Okay, so a toggle of a 0 is going to output 1. Toggle of a 1 is going to output 0. It's like NOT, basically, in the classical sense. Yeah. So when I was saying this, that Alice has access to the first qubit, Bob has access to the second qubit. Let's see what I mean by this. So what I mean is that suppose Alice toggles her qubit. Okay, then the EPR state initially was this 0, 0 plus 1, 1. If Alice toggles just her qubit, what the state becomes is a 1, 0 plus 0, 1. So just the first bit gets toggled. Okay, so now can you, so now what is going to happen if Alice actually measures her qubit and she sees a 1, then you know that Bob must see a 0. Whereas if Alice sees a 0, then Bob must see a 1. That is what's happening now. Okay, so you start off with an entangled state. If you do make this operation, you are still going to get an entangled state, but it might behave a bit differently with each other. Like how they are related changes, but they're still entangled. Is this clear? Is this toggle gate or operation clear? So on a single qubit, it just switches, it toggles 0 to 1, 1 to 0. But then on an entangled state, it is toggling just one, the qubit that Alice. So if Alice toggles, only her qubit switches. So what you get is still an entangled state, which is related differently. Similar for Bob also. Very good. Okay. So yeah, so if Bob toggles, it's like if Alice sees 0, then Bob is going so. But now see the cool part. If Alice toggles, the state that you get is exactly equal to the state that you get when Bob toggles. What is this? This is as though, so this is where the power of quantum comes in. This is as though, like even though Alice and Bob are in two different rooms, if Alice wants Bob to toggle his qubit, she can sort of simulate that by just toggling her own qubit. Okay. This is where the power comes. Let's see one other thing, one other operation, okay, which is rotation. Okay, so rotation of angle theta with on 0 will give you this, and the definitions are okay. Why that comes in, we'll just see in the next slide. Okay, but for now, let's believe this definition. Okay, and we do the same thing. So now, if Alice performs a rotation by theta on her qubit, what happens is just the first qubit gets rotated. Okay, and the second qubit stays as so 0. So rotation on 0, 0, rotation on 1, 1. And if you just open it out, you get this. Okay, so cos theta 0, 0 plus sin theta 1, 0 minus sin theta 0, 1 plus cos theta 1. If you just replace the values. Oh, sorry. Repeat one. Sorry. So Ria, repeat once. Which one? The previous slide? Ria, can you? Was it the previous slide or the rotation slide? Previous slide. Okay, I'm guessing previous slide. Okay. So actually, can you unmute and tell me which part you want repeated? So the
Yes, ma'am.
toggle. Yeah. Yeah.
Yes, ma'am. Can you hear me?
Yes, I can.
Okay, ma'am. Which is written in the blue ink?
Blue
I
part.
can't
Okay.
understand that.
Okay. So what do you only mention, right? That when Alice toggles her qubit, you got 1 0 plus 0 1. Okay. And if Bob toggles his, then the second bit gets flipped. Okay. But you see that if Bob toggles his qubit, you get a 0 1 plus a 1 0, which is the same as writing 1 0 plus 0 1. No. So these two qubits are the same, right?
Yes, ma'am. Same.
So what is that sort of telling you? It's saying that suppose Alice wanted some operation to happen on Bob's side. Okay. Because the two qubits are entangled, it is as though Alice is making Bob do something without him actually doing it. So suppose Alice, for some reason, wanted Bob to toggle his bit because she needs that to carry out the strategy. But she can't tell him, right? Because he's in a different room. But if she toggles her own bits, it is
Same.
it is simulating Bob toggling his bit.
Yes,
That's
yes.
what is it
Okay,
clear?
okay.
Yeah.
Yes, ma'am. It is clear now.
Yeah. That's what I was saying. So similarly in the rotation also we'll see how she can do something to make Bob do something. Okay, so in rotation, this is the operation that happens. Rotation by angle theta on 0 is cos theta 0 plus sin theta 1. And rotation by theta on 1 is minus sin theta 0 cos theta. Okay. Similarly, you start off with EPR pair. Alice performs, if she does rotation on her qubit, you get, if you just substitute the value of root of 0 and root of 1, you will get this qubit, which is cos theta 0 0 plus sin theta 0 1 0 minus sin theta 0 1 plus cos theta 1 1. Now let's see what happens if Bob performs. So in that case, rotation is going to happen on the second qubit. And you get cos theta 0 0 plus sin theta 0 1 now instead of 1 0. And minus sin theta 1 0 plus cos theta 1 1. I'm hoping all of you know these relations between what cos of minus theta and sine of minus theta is. Okay. By seeing this, can you tell me what is the relation? So Alice rotating by theta is same as what?
Bob rotating by 90 plus theta.
Exactly. Minus, yeah. Okay, so Alice rotating by theta is the same thing as Bob rotating by minus theta. Yeah, so again, it seems like if Alice wants Bob to do something, it seems like she can do something to simulate that on her side itself. In general, so these are just some of the transformations I mentioned, right? So this slide is I think, I mean, you would need to know a little bit of linear algebra to understand this statement, okay? But you can ignore that, okay? This I've mentioned just for people who know what unitary matrices are. I'm not going to, actually I can, okay? So unitary matrices are essentially matrices which keep, so if you start off with a qubit and you apply a unitary matrix on it, it stays a valid qubit, okay? But yeah, I mean, I don't want to spend too much time on this red part of it, okay? If you understand what unitary matrices are, good for you. If you don't, just ignore, okay? But it turns out that every quantum transformation that can be realized physically can be written as a unitary matrix. So if you want to have a k length qubit, performing any quantum operation on k length qubits is the same thing as multiplying a vector version of that qubit uh, with a 2 to the k cross 2 to the k unitary matrix. Okay, it turns out that the space of all unitary matrices exactly capture quantum transformations that can be realized physically. That's all this red thing is saying, okay? Which is why it just boils down to math essentially. So like we don't have quantum computers yet, and yet quantum computation is a full-blown area. Why? Because we just assume that we are doing matrix operations on, okay? Which is why we can go ahead and do quantum computation even though we don't have quantum computers. So that's the only reason I wanted to say this. But you don't have to understand what unitary matrices are and all. Okay, but let me just sort of tell you where little bit I want to say is that, so this ket 0 qubit is actually equivalent to a 1 0 vector. Okay, vector 1 0. The ket 1 vector, ket 1 qubit is equivalent to a 0 1 vector. And these two operations that we did, for instance, so toggle is essentially just saying that you multiply this vector with the matrix 0 1 1 0. And similarly, the rotation operation is just multiplying this matrix by the usual rotation matrix. Okay, so but this was just to bring in why those definitions came up. Okay, it's okay if you didn't understand this slide. Okay? This is just to tell you where the math comes in, or why we can do quantum computation without quantum computers. Okay. So now that we are, can you please share record? Sure. Yeah, sure. Sorry. Okay. So yeah. So now I think we have all the things that we need to understand the quantum strategy. So let's just dive into quantum strategy. Hopefully, I'll be done in 15 minutes. Okay. So one final time, what was the game? Charlie went, tossed coins. If the coin toss was head-head, then they win. If the answers are different, in all other cases, the answers should be same, then only they win. Classically, you cannot do better than 75%. And we will now show that if they have access to EPR pair, then they will actually win with probability at least 80%. Okay. So what is the quantum strategy? The quantum strategy is quite simple actually. So if the coin toss results in tail, then Alice will do nothing. Otherwise, she will rotate her qubit by minus pi by 8. Okay. And then she will measure. If it outputs 1, then she will say keep. If it outputs 0, she will say not. Similarly, Bob will if the coin toss is heads, then Bob will do nothing. Sorry. It should be tails. Sorry. Okay, so if it's tails, so he will do the same thing as Alice, except that instead of rotating by minus pi by 8, he will rotate by pi by 8. Rest of it is the same. Okay, so if it's tails, they do nothing. If it's heads, then Alice rotates by minus pi by 8, Bob rotates by pi by 8, and then after that, they measure. If the measurement outputs 1, they say keep. If the measurement outputs 0, they say not. Is it clear what the quantum strategy is? It's very simple strategy actually. Tails do nothing, heads, Alice rotate by pi by minus pi by 8, Bob rotate by pi by 8, and then measure. And the claim is that with this strategy, the thing is that throughout now this is heads. Okay, after this I will not be making this head into tail. Okay, it is that it has to be a tail. So when tail happens, Bob does nothing. So the claim is that with this strategy, it is going to become they will win with probability at least 80%. Is the strategy clear? Please let me know if not. Okay, I'm assuming the strategy is clear because yeah, it's not nothing hard. Okay, so so let's just quickly go over the cases then, right? So suppose the coin toss results in tail for both. Okay, then in this case, what was it? Both of them are not going to do anything. They are just directly going to measure, right? So if they are directly going to measure, then since they are entangled, they will be answering the same thing, right? So it's either going to be both are going to measure 0 or both of them are going to measure 1. So in this case, they actually win always. So in the case when the coin tosses are tails for both, Alice and Bob always win in this with this strategy. I'll just wait here for 1 minute, or not 1 minute, I mean few seconds. Let me know if you have any doubts. Is this clear to everyone? Okay, so in the case when both of them are tail, they just win always. So case 2 is when, let's say Alice has tails and Bob has heads. Okay, so in this case, what happens? Alice is not going to do anything. She is just going to measure. Bob, on the other hand, is going to rotate by pi by 8 and then measure, right? So now what is the, so now if you remember the rotate wala, what the qubit looks like, if you just substitute, what you will get is that this is the new state. The new state is cos pi by 8 0 0 plus sin pi by 8. This is what was happening when Bob was rotating by theta. In particular, theta is pi by 8. Okay. Once you have this, right? Is this clear? So Alice was doing nothing, Bob was rotating by pi by 8. So now what is the probability that they are going to answer consistently? That is, what is the probability that they are going to be either here or here? It is just, so note that this is unnormalized. Okay, so if you normalize it, this actually looks like So because cos square plus sine square is going to be 1, so this part has to be 1, the next part has to be 1. So actually all of them get multiplied by. So if you normalize, it becomes like this. Sorry. Okay. And it turns out that, so cos square plus, so because there's a 1 by square root 2, it's actually, it just becomes cos square pi by 8, which is at least 0.85. Is this clear to everyone? How we got to 0.85 in this case, the probability of winning? Again, I'm assuming it's fine because, again, if you understood till now, what I'm saying now is not very different. Okay, so case 3 again, it's the same thing, just opposite, right? So we will get the same probability, which is 0.85. Okay. Final case is when both of them have head. In this case, what happens? Both of them are going to rotate, right? So Alice is going to rotate by minus pi by 8. Bob is going to rotate by pi by 8. I am not showing the calculations. We are going to just substitute those rotation things individually on the 2 qubits. When you do the calculation, you can check that all the 4 actually happen with same probability. So I'm not going to do all the workup because you can do it on your own. Okay. And so therefore basically the probability of Alice and Bob answering differently becomes 0.5. Okay. So combining all of this, what do you get with this strategy? Sorry. With this strategy, oh, again, what did I? With this strategy, the win probability is at least how much? So the first one was, so in this case, when both of them were tails, they were always winning. So 0.25 into 1. In both these cases, they were winning with probability 0.85. So 0.5 times 0.85. And the last one, they were winning with probability 0.5. Okay. And if you do the calculation, it comes out to 0.8. And this is, of course, there was an at least here, which is why this is also an at least. Okay, is it clear? I hope it's clear. And this last part was just calculation, but yeah, what I wanted to sort of tell you was this, just this building up of these quantum things, give you some idea of what quantum gates look like, what, okay. So at the end of it, this is what we have seen. So when the quantum people were just first time that they were looking, they were seeing these anomalies and trying to understand what quantum mechanics is, they just felt like they are missing something because it just seems unnatural that there are entangled states, and they believed that any quantum experiment can actually be simulated using randomized algorithms if you are clever enough randomized algorithm. But this game was the first time that people realized that no, that quantum gives more power. You cannot explain away entanglements using some randomization. Okay, so this was sort of the main point in my talk. I will just quickly tell you a little bit about theory CS in general, which is the area that I work in. Okay, so in general, what does theory CS do? It basically takes a problem that needs to be solved and you build a mathematical model that describes what restrictions you have for the solve. So this is what I was saying, what I meant when I was saying that quantum computation exists even though quantum computers don't. Earlier, theory CS existed even though computers didn't. So theory CS is much older than the first computer, right? So in theory CS, we don't really look at, like, we don't care about whether physically there is the model is actually present. It's a completely mathematical model that we work with. Okay, and in that mathematical model, we want to solve problems. We want to come up with algorithms. And what we want to do is we want to study how much resource is needed by this model to solve this problem. So problem A, model B, we want to understand how much resource is needed to solve problem A by model B. Okay. And very high level, theory CS gets divided into sort of two parts, where whether you are more interested in solving the problem versus, so okay, now yeah, solving the problem, the kind of problems can be varied. Like, do you, as simple as finding the factor of a given number, like how fast can you find factors of a given number, to finding what the how fast can you find the shortest path between two vertices, or what is the best move, next best move in the chess game, or now we are going into learning category, right? But what is the best algorithm to differentiate an image of a dog or a cat? What is the next best word in a sentence, which is your LLMs, right? So all of this sort of, these are all problems that need to be solved. I want to solve these problems. I don't care about the model as such. I just want to solve these model problems in some model. Versus, it is the model that I'm more interested in. So it's like, I want to understand what all this model can do, what all this model is not capable of. Okay. So you have communication models where you have Alice Bobs, you have a Charlie, so two-party, multi-party, where the channel through which they are talking to each other, they can be compromised. So as in, there can be a hacker who's sitting there seeing what communication is going on, or there might not be. Okay. Then you have, when people are talking to each other, are they talking to each other directly, or are they broadcasting? So is it like a TV in which when someone speaks, everybody gets to hear, or are you doing a phone call? Are you just talking to one person? So each of these are different models. There are problems that can be solved in one, that can't be solved in other, more resources needed in one, less resources. So then you have, of course, computers, which are normal Turing machines. You have quantum computers, you have circuits, you have proof. Yeah, there are lots and lots of models. So broadly gets divided into, are you interested in just solving the problem and just brute force doing something, versus are you more interested in understanding the model, what all can be done, what all cannot be done. And complexity theory is typically the second. So when you're trying to understand the model is what complexity theory is more focused on, and that's sort of what I do. And so the kind of resources that we look at, for instance, when you have general computers, which is Turing machines, then you have the resources will be like time. How much time does the algorithm take? How much space does the algorithm need? How many random bits do you need? How does the algorithm need? And when you have circuits, so when you want to build circuits to solve a problem, then it's like, how many and or not gates do you need? If you have quantum circuits, then how many quantum gates do you need? If you have proof systems, I'll not define it, but there it's like you want to prove that something is true or false. Okay, so then how many lines do you need in the proof? So this is also something that is studied. Then you have a query system where you want to, like, you have a prover sort of, and then you can ask queries to the prover and make sure that the prover is not like faking it. So then, like, how many queries do you need to ask the prover to make sure that the prover is actually proving the correct statement that they're claiming? Then you have in the communication model, it's like how many bits have been exchanged. So how many times are you using the phone, or how many times are you using the broadcasting channel? So how many bits have been exchanged? So these are the kind of resources that we study depending on which model we study. And uh, clearly statements of the type that problem A can be solved by model B using at most this much resource. So if the problem can be solved by a model using small number of resources, that's always good, right? Then it can be converted into a proper algorithm, and then people will code it up eventually, and hopefully it will come out for general use. That's always good. But what I want to claim is that the opposite kind of statement, that is the amount of resource needed by model B to solve problem A is at least something, is also important. Okay, why? Because many times once you realize that, oh, this is actually a hard problem to solve, you start asking questions like, is it actually necessary to find the exact solution, or is it okay if I give a solution which is more or less optimal? And this leads to new areas like approximate algorithm. Then you ask, you know, is the maybe in the full generality this is a problem is hard, but in the real world situation, is it the full generality problem that you're trying to solve, or are there some additional restrictions? So if you have, this again is a full blown area called parameterized algorithm. And most importantly, one of the closest to my heart, is that if you know the limitations of the power, okay, then you can use that to come up with secure protocols, which is the full area of crypto and secure computation. Okay, so the fact that somebody cannot do something in less amount of time is then used to come up with security guarantees. Okay, so what I just wanted to say is that both kind of statements are actually very useful. One, that things can be solved fast or with limited less amount of resource, but if you can show that no matter how much or how smart the designer is, they can never come up with strategies which are better than, something, that they will always need at least this much resource. That also leads to something good, which is that you can use that to come up with security. Okay, so this is a very just quick summary of the kind of problems I work on and kind of things I do. And yeah, so because I'll be moving to NISER, I just want to advertise that we are a very small department right now, but we are trying to grow, and I would urge all of you to like apply there for PhDs, and yeah, that's it. Oh, oh my God, what is happening? Oh, thank you.
Thank you so much, Prerna, for the very nice talk and this brief intro to theory CS. So there is a question actually in the chat, if you can.
What is So Bell's theorem is this Bell's inequality that I mentioned. That it in classically you can never do better than 75%. So, but in his paper, he actually, I mean, yeah, that's where you come up with the quantum thing, and show that the quantum gives you advantage, whereas classically you can only do 75%. That's what Bell's theorem is. It just comes with different names. Some people call it Bell's inequality, some people call it Bell's theorem.
Any other questions? So could you suggest some resources for the students, books maybe, or something like that?
For quantum, yeah, so quantum specifically, actually, there's a very good set of lecture notes, as well as it's there on YouTube also. So Ronald D. Wolf. So let me maybe write. So he has a very good set of lecture notes, as well as he has a YouTube playlist on like I think something like quantum computation in 100 lectures or something like that. Which so these are like shortish, so 20-minute lectures, but 100 of them or something, which cover. So that's actually quite in depth. So this is specifically for quantum computation. In general, I think just if you want to do intro to theory CS, then some very good things are like
First, thanks to your.
Sorry, please go ahead.
No, sorry.
Oh, okay. So Boaz Barak, he has a book by this name only. So I think it's not published yet. It's there on his webpage. So Intro to TCS by Boaz Barak, and there is Mathematics and Computation by Avi Victorson. This is a very so this is a very general type of book, which I mean he doesn't go deep into anything, but it like sort of covers the full history of what theory C has, the full history of theory C, because it's not very old. I mean it was born in what 1920, right? So it's barely been 100 years. So he gives a very nice history of the full picture, full thing that has happened since the time of Turing till now. Whereas this one is a textbook. Okay, it is still in. Yeah. So the links have been given. Yeah. So what is P versus NP? I see. P versus NP is, so P is the class of all problems which can be solved efficiently by Turing machines. So efficiently meaning, so suppose, so Turing machines or just computers, basically the way we analyze how difficult a problem is that you give, so the input length, suppose is n, okay, right? So in the sense that you want to say, you give a string and you want to check if it's a palindrome. I'm sure many of you would have seen this problem, okay, or written a code for it. So the input length being n means like what is the length of the string. Okay, so in terms of the length of the string, P are all those problems or problems that can be solved in time polynomial in n. Okay, so if the input length is n, then if there is an algorithm to solve this problem in time n to the c for some constant c, then this problem is said to belong to the class P. So the P is the class of all efficiently solvable problems. Okay, and NP is non-deterministic P. It is not P. It is non-deterministic P. Okay, so non-deterministic P is the set of all problems or the class of all problems for which if I gave you a solution, then you could verify it quickly, like a Sudoku, right? So if I gave you the solution of a Sudoku, then verifying it is easy, but coming up with a solution, as again, so 9x9 Sudoku is something, but all of this is always in terms of the input length n. Okay, so like as the size of the Sudoku keeps increasing, it becomes harder and harder to solve. I mean, there's no algorithm to solve it in poly n time. Okay, but if I gave you a solution of the Sudoku, there is an efficient way to just check if all the rules of the Sudoku is verify if it is a valid solution to the Sudoku. Okay, so non-deterministic P are the class of all problems that can be verified easily. We don't know if anything that can be verified easily can also be solved easily. That is the P versus NP question. So our efficiently verifiable problems also efficiently solvable. That's the question. Partition of an integer meaning factor. So factoring is not, I mean, it's not known to be in P. We don't expect it to be in P. If partitioning is that, by partitioning, if you mean factoring, then I don't know what you mean by partition.
I think he means integer partitions probably.
What is integer partition?
So it's just the number of ways of writing down n as a sum of different.
Oh, I see. Like that.
Yeah.
Okay. Partitioning n into parts. That is not one of the classical, but that I'm not sure whether it's simple or not. Like finding all the parts. No, it should be easy to do actually. Maybe I think it
I think
should
there is
be.
a canonical way that you can do it.
Yeah. There's a canonical way you should be able to do it. So maybe it's in P. Yeah. It's not one of those classical problems, but yeah.
Any other questions? Okay, if not, then let us unmute and give a round of applause for Prerna for the nice talk.
Thank you.
Thank you so much for attending the talk, everyone, and especially Professor Chatterjee for giving this very nice intro. We hope that we'll get more opportunities to listen to you in the future as well.
Yeah, thank you.